Welcome to our video on the listening brain, which my team and I have put together for the York Festival of Ideas 2021. My name is Sven Mattis. I'm a professor of psychology of language in the Department of Psychology at the University of York. Together with the other members of the Speech Lab, Lyndon, Ronan, Alex and Sarah, we'd like to give you a brief overview of the wonders and challenges of something we all do several hours a day, listening. Intuitively, we all know the difference between hearing and listening. Listening engages not only the auditory system, but also more complex interpretive functions such as attention, memory, and intention. Taken together, these more complex functions are known as cognition. So a key notion here is cognitive listening. We can study cognitive listening in the lab by measuring behavior in response to sounds played in a quiet and controlled environment. So we can do soundproof lab research. But if we really want to understand how the brain and the ear work together to deal with natural soundscapes, we need to allow noise and disruptions in our experiments. So we need to do real-life speech research. And that includes understanding the contribution of memory, short-term and long-term memory, noise, how do we decide what is noise and what is not, then filtering, how do we filter out what we think noise is, or how do we filter out distraction, divided attention, how do we focus our attention on the voice that matters? Or how do we decide whether more than one voice needs to be paid attention to? And effort. How can we minimize the effort that goes into listening so that we have enough cognitive resources left for other activities, such as driving or paying attention to dangers around us? So we won't be able to cover everything in this video, but here are some of the questions we'd like to address. First, what kind of challenges do listeners face? What does our brain do when we listen? How can we measure effortful listening? Can the brain fill in gaps of information when the information is simply not there? And can we truly filter out noise? And at this point, I'd like to hand over to Lyndon.
Hi, I'm Lyndon Maxson. I'm a research assistant here at the Speech Lab, and I'm going to be talking about some of the difficulties the brain faces when listening. So the brain's got a long to-do list of things in order to get useful information from our ears. So it's got to combine sound from both ears, coming in at the same time, locate the point of origin of a sound, direct our attention to important sounds in the environment, perceive and understand speech, so separate it out from general sounds, and deal with adverse listening conditions. So there's too many things to talk about here for just this presentation, so I'm going to focus on how the brain deals with adverse listening conditions. So one of these adverse listening conditions is poor signal quality. So this is when a sound is missing important frequencies for comprehension and has a low amplitude. So a good example of this is when you're underwater. So if you've ever been swimming and had someone trying to talk to you from above the water, you'll find that their voice is all muffled and it's quiet and it's just difficult to hear what they're saying. This is because sound doesn't travel well between mediums, at least doesn't come through between mediums intact. So it'll be missing some of the important frequencies you need, and it'll also be quite quiet. Another example of this is when you're trying to listen to something through a wall, or maybe not intentionally, but if you're hearing music from an adjoining room, you might just about hear what the song is, but a lot of those frequencies will be absorbed by the wall, and it might be a lot quieter than it otherwise would have been. And finally, if you've ever had a bad phone line before, it can be impossible to hear what the other person's saying. They might be just too quiet, and no matter how much you turn the volume up, you just can't hear what they're saying. Or they might be very tinny or muffled, and those particular pitches and frequencies you need to understand speech aren't there. So in some ways, this is the most difficult listening condition of all. So another listening condition, adverse listening condition, is energetic masking. So this is when you have multiple sounds in the environment and they're happening at the same time, but only one of those is what you're interested in. So we've got our green sound here in waveform and our red sound, and we're only interested in the green sound, but they're both happening at the same time. So in this situation, they'll be overlapping in amplitude. So one of the red sound is just as loud as the green sound, and that makes it kind of hard to separate out, and a lot of the frequencies are the same. That's another thing that the brain would otherwise use to separate the sounds out into two separate sounds. And this affects the audibility of the target sound. Another kind of adverse listening condition is informational masking. So this is not energetic like energetic masking is. This is more to do with cognition. So a good example of this is when you've got multiple people speaking at the same time. You may only be interested to listen to one of these conversations, but all the sounds are going into your ears, and your brain's got to separate out the irrelevant speech with the relevant speech. It has to do this by grouping the two speakers into separate streams, but this isn't always easy, and you may get words mixed in with the other words from the speaker you do want to listen to, and this can make it difficult to understand what the person is trying to say. Yes, so it affects intelligibility rather than audibility specifically. So, one final adverse listening condition is cognitive load. So, it's to do with divided attention. So, the brain's only got a limited amount of attention it can devote to any one stimulus. So, in this case, you might be listening to some speech, which is perfectly audible. There's no other sounds going on in the environment. Normally, you would have no trouble understanding and hearing this. But if you're trying to do another task at the same time, so this doesn't even have to be a listening task, it could be a visual task. So perhaps you're trying to do some complicated sums, trying to drive your car and concentrate on the road, or look for a missing person in a crowd. This could all impact your ability to understand speech, just because you're not able to devote enough resources to comprehending speech. They're taken up by the visual task. And this affects our perception of speech and the audibility and the intelligibility. So what have we learnt so far? We've learnt that listening is challenging. It's amazing we actually hear anything at all. So the brain must be doing some important processes, some important cognition in order to allow us to find the things that are important in the world of sound and concentrate on them. So what is going on in there? And how can we find out? So for these two questions, I'm going to pass you on to Ronan, and then Alex will follow up after that.
Hello there, my name is Ronan McGarrigle, and I'm a postdoctoral researcher here in the speech lab at York. So we talk about cognitive listening and the listening brain, but how do we actually know that the brain is even doing something when we listen? And more importantly, how can this be measured? So when we hear speech, unsurprisingly, our ears perform the first set of operations. That is, they help to transform acoustic energy into electrical signals that are sent to the brain. But which parts of the brain receive these electrical signals? And secondly, how do we actually measure this brain activity? Well, functional magnetic resonance imaging, or fMRI, can tell us which parts of the brain become activated by measuring changes in blood flow when we listen to speech, offering what we call spatial precision. And from this, we have learned that there is typically widespread activation in the brain when we listen to speech. But areas that show most activity include superior temporal regions, including the auditory cortex, and also frontal regions. And this part of the brain is important for various cognitive functions like memory and attentional control. And as Sven mentioned earlier, we know that speech understanding relies heavily upon these cognitive processes. However, one of the potential disadvantages of this technique is that MRI scanners are typically quite noisy pieces of machinery. And of course, as auditory researchers, we do like to have a high level of control of the sound environment during experiments. Okay, but what if we were not necessarily interested in where activity in the brain takes place, and instead we wanted to ask a slightly different question, and that is, how hard is the brain working? And in particular, how much extra work does the brain have to do in normal everyday listening conditions where there is typically lots of background noise and distraction? So lo and behold, we can find out how hard the listening brain is working by looking at the eye. And in particular, we can measure how much mental effort someone exerts during listening by recording changes in the size of the eye's pupil. So increased pupil size reflects increased listening effort. And this technique is called pupillometry. In order to record these very small changes in pupil size, we use an eye tracking device like the one you see here. Eye trackers are fairly silent and non-invasive, so they don't interfere with our auditory stimuli and can easily record information in the background. So what typically happens in the lab is that we ask participants to look at a fixation cross on the screen, and we record their moment-to-moment changes in pupil size while they listen to speech. And here is typically what we see. So when someone listens in an ideal listening condition, like for example in quiet, we tend to see a relatively small increase in pupil size to reflect the sort of limited effort required. But if we present the same kind of speech stimuli, but this time in the presence of background noise or people chattering in the background, we tend to see a relatively larger increase in pupil dilation, reflecting the increased effort required in this kind of scenario. Okay, so let's have a look at a real-life example of a study we conducted in the speech lab. So we were interested in the question of whether or not older adults have to work a little bit harder to understand speech in the presence of noise. So we had an easy condition with low levels of background noise and a hard listening condition with relatively high levels of background noise. And you can see here that in the young adults, pupil size was relatively larger in the more challenging listening condition, and that's what we would have predicted. And we actually saw a fairly similar pattern for the older adults, but importantly you can see that overall, so across both listening conditions, their pupil dilation was relatively larger than the young adults. And this sort of suggests that older adults do indeed have to work that little bit harder just to understand speech in the presence of distracting noise. So to summarise, pupillometry appears to be a potentially useful technique that we used in the speech lab here at York to reveal just how hard the listening brain is working. And next up, Alex will talk in more detail about what the brain does when listening to different types of auditory stimuli.
Hello, my name is Alex Mepham and I am a PhD student in the speech lab. Our brain is a complex interconnected organ with some areas of the brain used for one primary function and other areas which are used for different processes. With the use of different techniques measuring brain activity, we are able to locate the brain areas used in specific types of tasks. We in the speech lab are interested in speech perception, and many experiments using brain imaging find that the brain area most often used in speech and sound perception is the temporal lobe, coloured here in red. Imagining the frontal lobe at the front of your head and the occipital lobe at the back of your head, the temporal lobes are at the sides of your head. What we find is that some areas in the temporal lobe are used for listening to different types of sounds, and for filtering relevant and irrelevant sounds. In this image of the brain from above, there are different blue and orange coloured areas which represent brain activity using functional magnetic resonance imaging that Ronan mentioned earlier. Here, researchers found listening to speech used specific brain areas coloured in orange, which were different to brain areas, coloured here in blue, used for listening to non-speech sounds. There is also a distinction found between listening to any speech sound and speech that is intelligible to the listener and that can be understood. In this image, researchers found differences in brain areas used between any types of speech sounds, marked in this image in orange, and speech that can be understood to the listener, which are coloured here in yellow. Researchers find that listeners are worse at understanding speech in noisy environments and have to use more effort while listening. And this is something that you might recognise yourself if you've been in a noisy cafe or a loud train station. The researchers have also shown greater brain activations in the areas used for speech perception when the background noise is louder, suggesting a greater recruitment of the brain's resources when listening in difficult environments. And it's these questions about how our brains process speech in noisy environments that are our key focus in the Speech Lab. But, as Ronan mentioned earlier, brain imaging can only tell us so much. These images are great at showing where the brain activations are when we are listening and filtering to speech in noise, but it doesn't tell us how accurate we are or how fast people are in able to understand and filter speech, or how much effort people use when listening to speech in noise, or how fatigued people become when listening to speech in noisy environments. And this is where we use different methods, like pupillometry, sentence recognition tasks, reaction time tasks, and self-report measures of effort and tiredness to ask different questions about how the brain processes and filters speech and noise. I will now pass on to Sarah, who will talk about filling in the gaps.
Hello, I'm Sarah Knight, and I'm a postdoc in the Speech Lab at York. So when you're listening to someone in a noisy environment, there will be moments when the voice of the person that you're trying to listen to is hidden by the background sound. However, if these gaps are only brief, that doesn't stop us understanding what's being said. Our brain works to fill in the gaps for us. In other words, listening isn't a passive activity with the sound simply entering our ears and travelling up to our brain. Instead, listening is a process of active construction. Or put another way, recognising speech requires a combination of sensation. You have to have heard at least some of the sound, but also memory. We use what we already know to fill in the gaps. This means that what we hear relies on our experience and our expectation. To some extent, we hear what we think we're going to hear based on a lifetime's listening. One of the key factors shaping our expectation is context. So in some situations, you can work out what's being said simply because the context is so familiar that you already know in advance. So for example, if somebody walks in carrying a cake with candles and starts singing a familiar tune, you might not hear all the words, but you can be pretty sure they're singing Happy Birthday. On other occasions, you don't know in advance what's being said, but you can use the rest of the sentence to work it out. So, for example, if you hear the phrase, "I put food in the dogs," and you didn't hear the final word, it's pretty likely to be bowl, but it isn't necessarily. It could be kennel, for example. So in those situations, you need to try to use those bits of the sound that you did hear to work out what was being said. Did you hear one syllable or two, for example? What kind of vowel sound was it? And sometimes you need to use the context around you as well as the sentence to make sense of what you've heard. So given the sentence, "Oh no, I broke a," something. If you only heard the ol part of the sound and you're in the kitchen, you'd probably think that the speaker had said bowl. But if you're out skiing, even if you heard exactly the same part of the word, you're much more likely to interpret it as pole. Let's have a listen to an example of this phenomenon in action. I'm going to play you a sound in which there are 8 women talking simultaneously and 1 man. Have a listen and see if you can work out what the man is saying. I'll play that again for you. Okay, I think you'll probably agree that it was pretty hard to hear the man at all, let alone what he was actually saying. So I'll tell you that the man was saying, a code is needed when secrets are sent. And here's the man's voice.
A code is needed when secrets are sent.
I'll play that again for you.
A code is needed when secrets are sent.
And now I'll play the original example again. See if it's any clearer. Here's the man.
A code is needed when secrets are sent.
And the version with the background noise. Hopefully, you will have found it a bit easier to hear him once you knew what he was saying and what his voice sounded like. It wasn't that you could hear any more of the physical sound than you could the first time round, but the expectations that you had allowed you to more successfully fill in the missing information. But sometimes expectation does more than simply fill in the gaps. In some situations, expectations can lead to completely different perceptions. Here's another example, and this uses a sound that we've created in the lab. So this is some randomly generated computer noise. I'll play it for you now. I'll play that again. Okay, I confess, it wasn't randomly generated computer noise. It was actually somebody speaking, but we'd manipulated the sound to take out a lot of the information that's normally in a voice. The speaker was actually saying, they say some silly things. And here's the original recording.
They say some silly things.
I'll play that again for you.
They say some silly things.
Now have a listen and see if the manipulated version sounds more like speech. Here's the original.
They say some silly things.
And the manipulated version. So hopefully, the manipulated version does now sound more like speech. So here, it's not that you can hear speech better once you know what to expect. In this case, your expectation is actually governing whether you hear speech at all or whether you hear a sound as simply random noise. And finally, it's important to remember that we're all different. We all have our own personal experiences and expectations, so we hear ambiguous sounds in highly individual ways. And this means that we don't always all hear the same thing. One very famous example of this recently was the Yanny Laurel debate that erupted on social media. This revolved around a recording of a single word, which some people heard as a fairly high-pitched voice saying Yanny, and others as a fairly low-pitched voice saying Laurel. In this case, different people's brains seem to be picking up on different parts of the sound, which in turn affects how they interpret what they hear. I'd strongly encourage you, if you haven't already heard it, to look up Yanny and Laurel on the internet and have a listen. It's a fascinating auditory illusion and a great example of how different people can have different interpretations of the same sound. Okay, so I've given you some examples of how cognition can help us in challenging listening situations, and more generally how it shapes what we hear. I'll now pass you back to Sven, who'll tell us a bit about how limits on our cognitive abilities can actually impact our hearing.
As Sarah pointed out, the listening brain is good at making sense of ambiguous sounds and filling in missing information. But it's also good at filtering out what it considers to be irrelevant, such as noise. And clearly being able to ignore noise is vital. But there is such a thing too as overfiltering. Most species have evolved to be able to control their auditory filter and let some background noise in, so that they can remain vigilant and aware of danger at all times. But we as humans have been living in a comparatively safer environment where alertness and vigilance are less critical for survival. And in fact, we are pretty good at completely switching off our auditory awareness to the point of experiencing what is sometimes called inattentional deafness. This is what happens, for example, when you are so engrossed in reading a book that you won't hear the doorbell ring, or chess players seemingly cut out from the rest of the world. So highly selective attention is an important feature of human cognition, which is essential during complex reasoning, for instance. But our ability to completely disconnect from the world when we perform a complex task is also evidence that we have limited cognitive capacity. Now, the idea behind limited cognitive capacity is that we each have a finite amount of mental energy that we can choose to invest as we see fit at any one time during cognitive activities. For example, if my personal cognitive capacity is 3, and I'm doing a visual task that requires 2 units of mental energy to be performed well, I will only have 1 unit left for any other task performed at the same time. If that other task, say an auditory task, requires more than 1 unit to be performed well, I will need to accept poorer performance on that task, or alternatively, poorer performance on the visual task. So during listening activities, we are constantly facing a cognitive trade-off. Take a hearing test as an example. Detecting a very quiet sound, a very quiet beep, which is what one does in a hearing test, requires full attention. What we found is that if someone is asked to do a standard hearing test and a visual task at the same time, the hearing test results will not be as good. They will show a small but measurable hearing loss. So taking the long view, what this means is that preserved cognitive capacity, good working memory and attentional skills can help deal with the challenges of noise or distraction. In fact, good working memory in individuals with hearing loss is associated, at least to some extent, with the benefit they can expect from a hearing aid. The better your working memory and cognitive skills, the greater the benefit you can expect from a hearing aid. So to sum up, in order to understand listening, we need to take into account working memory, maintaining information as we hear it, long-term memory, recognizing target speech, and attention, being able to filter noise. This is cognition. These cognitive components interact with each other and serve behavior, hearing, seeing, and reasoning. But as we said, the capacity available within the cognitive system is limited, which means that if we are performing 2 tasks at the same time, those 2 tasks will compete for cognitive capacity. And if we are performing 3 tasks, cognitive support will be even further limited. Well, this is the end of our presentation on the listening brain. We hope you enjoyed it. We would like to acknowledge the Leverhulme Trust and the Economic and Social Research Council for funding some of the research described in this presentation. Thank you.